So we break our elements into two main categories, metals and nonmetals, and then we have a third category in between the two of them. For metals, metals have bright lusters. So our mirrors have been made at various times in the past from just polished metal, polished silver metal, silver plated on the back of glass. So the bright luster is just this reflective surface that we get from the metals, from a polished metal. Metals tend to have high density. They have high melting points. That's why we can use iron pans, aluminum pans, titanium pans to cook our food. We put the heat on and they do not melt. But they're also good conductors of heat, so we put on the heat on the bottom and the heat goes right through to the top of the metal pan. Metals are also good conductors of electricity. This is one of the defining characteristics of metals, how it conducts electricity. Metals tend to be malleable and ductile. That means that when you hit them with a sledgehammer, they bend instead of breaking. And ductile means that you can pull them into a wire shape. Most of our elements are metals, and they're all solids except for our one liquid, one mercury. Nonmetals, they tend to be, we don't have as many examples of nonmetals floating around for our daily use. Most of our nonmetals are compounds instead of pure elements in terms of our solid forms. But nonmetals are more likely to be dull, not always. Sulfur would be dull. Carbon comes in two forms. Graphite, which is dull, and diamond, which is pretty. Most nonmetals will have a low density, low melting point. And low melting point is why we don't have as many examples, because a lot of the nonmetals are gases. They have melted and they have vaporized and they're gases. So our air is mostly nitrogen, a nonmetal, oxygen, a nonmetal, then it has traces of argon, a nonmetal, and then some other compounds. The nonmetals tend to be poor conductors of heat or electricity. So we are experimenting with using diamond in our semiconductor industry because of its ability to be a good electrical insulator, heat insulator. We use compounds made out of nonmetal ceramics as heat and electrical insulators. Nonmetals tend to be brittle, so if you hit a diamond with a sledgehammer, the diamond doesn't bend, it shatters. So we have only 17 elements that are nonmetals, 5 of them are solid, and 11 of them are gases. Only one of them is a liquid. Our semimetals, we take these from the border of our metals and nonmetals. So we take some of the metals, some of the nonmetals, and we classify them as semimetals. They have properties in between metals and nonmetals. So if metals are good conductors of electricity, nonmetals are insulators of electricity, semimetals are semiconductors, and this is what we use in our semiconductor industry. We started off with silicone, and then we dope or spike the silicone with germanium or arsenic or other elements to modify the electrical properties as to when they switch between conductor or insulator. For chemistry, we have a law of conservation of mass. We do not create or destroy matter. So the mass of the reactant is going to equal the mass of the products. The mass before the reaction will equal the mass after the reaction. We've done this even though it doesn't always appear that way. So when we burn a candle, we start off with maybe a 10-gram candle. After we're finished, we have nothing left. It looks like we destroyed matter. But if we do a full accounting of what happens, we see that it consumes oxygen from the air and produces both carbon dioxide and water. And when we account for all those, the mass does not change during the chemical reaction. And the examples on the bottom is also show that during our chemical reactions, they react in specific ratios. That ratio can be multiplied to larger numbers, but it can't be shifted. So when we are combining hydrogen with oxygen to produce water, we have this ratio of 1 to 8. 1 gram hydrogen to 8 grams oxygen to give us 9 grams of water. And if we try to change that ratio of what we have in terms of hydrogen and oxygen, we don't change the amount of water that we can get, but we'll have some excess reactant left over. But the total mass before and after the reaction will remain the same. So from our chemicals, from our elements, we have a variety of elements. Let me go back and that periodic table again. So our periodic table here, doesn't identify the elements that are natural or man-made. We had natural elements up to element 92, uranium. All the elements past 92 are synthetic. We made them in a variety of processes. Linear accelerators, cyclotrons, nuclear reactions, nuclear reactors. So they are all synthetic. So, and even the 92, we didn't have all the elements going to the 92. We were missing technetium and promethium. So 43 and 61. So we start off with 90 natural elements before the nuclear age. Since the nuclear age, we've been making additional elements. We're intentionally trying to make them and prove them. And we have gotten up to element 118. Although we are still currently missing element 117. So we have a total of 117 elements up to a number 118. And these higher elements, the real high elements, have extremely short half-lives. They disappear in fractions of seconds after they're made. Down here, the transuranium elements on the bottom ones, these can last a long time. Some of these can last a long time, and they are part of the radioactive waste of nuclear reactors and nuclear explosions. So from our elements, so we have a maximum 117 elements to play with. From our elements, we can combine them together to make compounds, and we can make millions upon millions of compounds from these 118 elements. So in our compounds, we have a law of definite composition. The compounds always contain the same elements in a constant proportion by mass. By mass, also in constant proportion by number of atoms. In our compounds, we have two types that we're going to be looking at, covalent and ionic. In our covalent compounds, the smallest unit is a molecule, and this is composed of two or more atoms bonded together in a consistent fashion. So this is not including metals, and it's actually not including ionic compounds. We call that a formula unit for ionic compounds. So molecules is the smallest unit of the compound. It contains the chemical properties of the compound. If we break that molecule into smaller units, the properties will change. So we represent compounds in both a name and a chemical formula. The chemical formula is going to be using the symbol of each element present, along with a subscript that shows how many atoms of that element is present in the compound. So some examples of compounds. NaHCO3. That means that we have 1 sodium, 1 hydrogen, 1 carbon, and 3 oxygens in this compound. The name would be sodium bicarbonate, or also sodium hydrogen carbonate, or the common name, baking soda. This is actually an ionic compound, so this would be a formula unit. So as an ionic compound, when we dissolve this in water, we'll have sodium ions floating, positive sodium ions floating around in the water, along with negative bicarbonate ions floating around in the water. Na2CO3, sodium carbonate, 2 sodium, 1 carbon, 3 oxygens. CO2, carbon dioxide, 1 carbon, 2 oxygens. CO, carbon monoxide, 1 carbon, 1 oxygen. Right here we just have the same two elements and change the ratio slightly. Does that make a different compound, or make one of them just a little bit more oxygen enriched? Well, it's a different compound based on what happens, its chemical properties. Carbon dioxide is a product of respiration, a product of combustion. We exhale it on a regular basis, so there's a bit of carbon dioxide in the air. We don't have a problem with it until it gets up to several percent composition. Carbon monoxide, however, is generally a product of incomplete combustion, so we don't have enough air when we're burning something with carbon monoxide. And at low concentrations, still in the part per million level, it'll poison us. It'll replace the oxygen in our blood, and we will die from it. So different chemical properties just by changing the number of oxygen present. We have CO, both capital letters, and CO, C is capital, O is lowercase. The difference, so each of our elements starts off with, consists of 1 or 2 letters normally. We have 3 letter ones that are temporary designations, but they always start with a capital letter, and if there's a second or third letter, those are always lowercase. So if both of our letters are capital, that means we have 2 different elements, carbon and oxygen. If the second letter is lowercase, it means we only have 1 element. We looked that one up, and CO is cobalt. So that would just be a pure element. CaCO3, that would be calcium carbonate, is a chemical name. The common form that we find it in is limestone or marble, our mineral names. HCO3 2. So this is another way that we do it. If we want to designate multiple ionic units like this, we put a parenthesis around it and then a subscript outside. That subscript multiplies everything inside the parenthesis. So we have 1 calcium, we have 2 bicarbonate ions. And if we're counting all the elements, we'd have 1 calcium, 2 hydrogens, 2 carbons, and 6 oxygens. COCl2, cobalt chloride, H2O water. This is the common name. It would have another based on our naming system, but we use the common name of water. H2O2, hydrogen peroxide. And again, we're just changing the oxygen level here. There are some people who like to claim that they have oxygen-enriched water, but if we were to change this oxygen amount in the water, we go from water to hydrogen peroxide. Well, we can drink water, hydrogen peroxide at 3%. We can put on our skin. We can gargle with it, but higher percent of hydrogen peroxide will burn our skin.